Okay, in the last video we learned that Dalton's law is really quite simple, that if you have a mixture of gases, the total pressure of all those gases is the sum of all of the partial pressures of the individual gases. And another way to think of Dalton's law often is more simply as the fact that the total pressure of the gases is directly related to the total number of moles of gas, no matter what type of gas it is. This works faster in some problems, this in others. But as a second example, and we have a few more to look at on this video, we know we have to apply Dalton's law because we have a 30-liter container that contains both 12 grams of nitrogen and an unknown mass of oxygen, a different gas. So right away I know I'm dealing with a mixture. Right away I think in terms of this and or this. Now, we can solve the problem either way. So let's try it this way first, and we'll compare it to that way, and we'll see which takes less time. And then maybe on the next problem we can predict which way to go and save time. Well, first of all, I write everything down. I write down the fact that I have 12 grams of N2 gas and an unknown amount of O2 gas, but they both occupy the same 30-liter volume container, and they both have the same 303 Kelvin temperature. Now the pressure I have to label. Is this the pressure here of just the nitrogen, or is it the partial pressure of the oxygen, or is it the total pressure of the mixture? Well, if the pressure in the container is this, and the container is holding two gases, this must be the total pressure of both. And the key to success in Dalton's law is labeling the pressures and the amounts of the substances and keeping track of them. Now in this problem we're asked for the mass of oxygen. And of course, we know that we can use the ideal gas law to get the amount of oxygen if we know its temperature, volume, and pressure. Well, we do know the volume of oxygen, we do know the temperature of oxygen, but we don't know its pressure. So if we could find the pressure, the partial pressure of oxygen, we could solve for the amount of oxygen. Now, let's first look at Dalton's law this way. If we have a total pressure, which we do, if we could find the partial pressure of the other gas, nitrogen, we could get the total pressure of the oxygen, because after all, the total pressure in this problem is the sum of the oxygen and the nitrogen's partial pressures. So to get this partial pressure, I would need that one in the total. I have the total. So I need to say, well, do I have enough information to get the partial pressure of nitrogen? And the answer is yes, because I know the amount, the volume, and the temperature. So the pressure of the nitrogen is 0.0821 liter atmospheres of nitrogen per each mole nitrogen Kelvin. And there's the partial pressure of the nitrogen. I need only cancel the volume, which is 30 liters, and cancel the temperature, which is 303 kelvins, and cancel the moles of nitrogen. Now, I was given a mass, but I can easily convert moles to mass and then cancel, because the molar mass of N2 is 28 grams per 1 mole. So the moles cancel, and I am left with a mass, but I can use my mass to cancel my mass. This gives us a partial pressure of nitrogen that is 0.355 atmospheres. So far, all I've done is use the ideal gas law and the amount of a gas to get its pressure. However, now comes the Dalton's law. However, the Dalton's law part, quite simply, is that the total pressure of a gas, and this was how much our total pressure was, is the sum of the two partial pressures. And the partial pressure of our nitrogen was 0.355 atmospheres, which means I can now figure out what the partial pressure of the oxygen was. It's the difference in the total and the partial pressure. So I grab my calculator, and when I subtract 0.355 atmospheres from the total, 2.55, I get a partial pressure of oxygen equal to 2.20 atmospheres. But this is not the answer to the question. We wanted to know what mass of oxygen we have, but now we have all the information we need to get our final answer. Because we know the volume of the oxygen, we know the temperature of the oxygen, we know the pressure of the oxygen. So one more application of our ideal gas law. There's a mole of oxygen Kelvin for every 0.0821 liter atmospheres of O2. And since we have 2.2 atmospheres O2, they cancel. We have a temperature of 303 kelvins, boom, boom, and we have a volume of 30 liters. So if I take my calculator and calculate how many moles of oxygen that is, I get one answer, but of course we wanted to know the mass. So one last conversion, 1 mole of O2 is the equivalent of 32 grams of O2. And so this calculation gives me my of 84.9 grams O2. Now my promise was that we could do any of these problems thinking two different ways. And here we used this version of Dalton's law. But we should also be able to solve the problem with the understanding that total pressure is simply directly related to total moles. So we're going to get a preview of the next problem while I redo this problem. Better yet, let me just pause for a moment and erase. So with a fresh start on the same problem, I'm instead going to take this route, that the total pressure is directly related to the total number of moles in a gas mixture. And so if we want to know what the mass of oxygen is, that would be pretty easy, because if we knew the total numbers of moles from this understanding, if we subtracted the moles of nitrogen, which we can calculate easily based on this information, we'll get the moles of oxygen and can convert it to a mass. So this may actually be a lot easier in this form of the problem, because the total number of moles can easily be calculated with the total pressure. There is a mole total of gas, Kelvin, for every 0.0821 liter atmospheres total pressure. And with 2.55 atmospheres total pressure at a temperature of 303 kelvins and a volume of 30 liters, everything cancels except the total number of moles, meaning this all comes out to 3.08 moles total gas. And of course, a fraction of this total is the nitrogen. And since a mole of nitrogen equals 28 grams of nitrogen, the molar mass of nitrogen, and we have 12 grams of nitrogen, it means that we have 0.429 moles of nitrogen. So if we have 3.09 total moles less the 0.429 moles that are nitrogen, it means that in fact we have 2.65 moles of oxygen in this mix. And since it asked for a mass of oxygen, and 1 mole of oxygen equals 32 grams of oxygen, when I multiply this out, I get, lo and behold, 8, slightly different answer, 84.8 grams of oxygen. And so once again, it matters not whether you use pressure to mole proportional relationships or you use the individual partial pressures. You can get a correct answer to any Dalton's law question involving a mixture. Now for a final example on this video, though there will be other examples forthcoming, consider the following reaction. Now we have a chemical reaction here between an ionic solid, or with an ionic solid, that produces another solid ionic compound and a gas. Now we decompose some of this solid to produce some of this gas. And the gas is collected over water. So I remind you that when you have a container that's filled with a liquid and you place it upside down over a liquid and you run a reaction and capture the gas under the container, it bubbles up within the container and is trapped there. I didn't mean to erase my container, just all the water that was there. We end up trapping our gas in the container because gas is less dense than liquid, and if you let it go under the liquid, it bubbles up, gets collected, can't go anywhere, but it does put pressure on the liquid beneath it and push it downward. So yes, we can capture and measure the gas that we create or generate from a chemical reaction such as this. Now please remember, this is a Dalton's law problem for one reason. In this case, yes, we'd have some oxygen up here because that's the gas that came through our tube and was collected. But of course, any liquid will necessarily have some of it vaporize above it and form a vapor of the liquid. So living up here with the oxygen gas is some water vapor. And even though we call it vapor, it walks, talks, and quacks just like a gas. So it behaves like a gas. So point being, anytime you collect a gas over a liquid, you end up with Dalton's law, a mixture of gases. And we want to know what the pressure is inside the flask. Now this problem is most easily solved with this version of Dalton's law, because we will have two things in that container exerting pressure. One will be the pressure of the oxygen we collect, the other is the pressure of the water vapor. And we're given the pressure of the water vapor. So since we have it, all we have to do is find the partial pressure of oxygen and we'll know the total pressure. And that's pretty simple because I just do some easy stoichiometry. We start with 10 grams of potassium chlorate, that I'll just abbreviate PC. And since we can only use moles stoichiometrically, I convert to moles. A mole of potassium chlorate is 122.6 grams of potassium chlorate, so we're dealing with moles. Now for the stoichiometry portion of the problem, namely for every 2 moles of potassium chlorate we react, we get 3 moles of oxygen. So 2 moles PC will give me 3 moles of O2. Boom, boom. So yes, we are done with the stoichiometry part of the problem. We know how many moles of oxygen are going to be up inside this container. Now all we have to do is convert it to the partial pressure of oxygen. And for that, I turn once again to my ideal gas law. There are 0.0821 liter atmospheres of oxygen for each mole of oxygen Kelvin. And yes, moles of oxygen cancel. And I get my partial pressure of oxygen if I simply cancel the volume. It was a 20-liter container after all. And I cancel the temperature, which was 323 kelvins. Lets me calculate that the pressure of the oxygen is 0.162 atmospheres. That's a 6 of oxygen. And of course, now I could get the total pressure in that container if I add the pressure of oxygen to the partial pressure of the water vapor. And the only problem confronting me still is that they're given in different units. That's not a problem. 1.162 atmospheres can easily be converted to millimeters of mercury because 1 atmosphere equals 760 millimeters of mercury. Meaning the actual water vapor exerts a pressure, or excuse me, my oxygen, which is what I was making the conversion on, exerts a pressure of 123 millimeters of mercury. And now I can get the total pressure because that's oxygen's partial pressure. Water vapors is 92.5 millimeters of mercury. And according to Dalton's law, when I add the 2 partial pressures, I would get the total pressure. And that total is 216 millimeters of mercury. Dalton's law.